All right, so now we are in section 11.10. We are going to be talking about Taylor and Maclaurin series, or Taylor and Maclaurin polynomials. This is definitely going to be a multiple video lesson. Some of these problems can take some time to go through, but it is important that we actually go through the process and how all this stuff is developed. So um, let's go ahead and get started. So the idea is a Taylor and Maclaurin polynomial is basically what we were talking about before, in the fact that we are going to be taking things which are not polynomial functions and creating polynomial functions out of them by using a Taylor series. First one we're going to talk about is this one which is called a Maclaurin polynomial. And I really hope that Maclaurin is the one who came up with this idea first and he didn't just rip this off from Taylor, because you'll understand why when we get there. But if he just said, oh, I'm going to take this Taylor polynomial and make it centered at 0 and call it my own, that's pretty, I'm actually jealous if that's the case, because I should have thought of something like that. Anyway, Maclaurin polynomial, it's the basic one. It says, if f can be differentiated n times at 0, meaning centered at 0, then we define the nth Maclaurin polynomial for f to be as follows. Now, the equation here looks a little bit cumbersome, but it's really not as hard as it looks. The notation is, this just means it is a polynomial that we're creating of n terms. That's all. It's a polynomial function of x, of n terms. This is your general notation. It's the one that will help you find any one of the terms. And the notation is, and this is important, because you might think, oh, it's f raised to a power. Remember that when we put the what looks to be the exponent in a parentheses right there, that is actually the derivative. So that's telling us the nth derivative evaluated at 0. So we're going to take a series that starts from n equals 0, where we find the nth derivative on top, divided by n factorial, multiplied by x to the n power. One of the things you should notice is that number, the derivative is n, the factorial is n, and that power is n. So all those values will be the same. And then when you start writing it out term by term, it'll just be literally the first value is going to be the function evaluated at 0. So the original function evaluated at 0. Then it's the first derivative over 1 factorial times x to the first. The second derivative over 2 factorial times x squared. Third derivative times 3 factorial x cubed, and so on. So you can hopefully start seeing the pattern there. So the polynomial has a property that its value and the values of its first n derivatives match the first values of f and its first n derivatives at x equals 0. In other words, all those values are the same. The derivative, the factorial, the power are all going to be the same. And these are all polynomials, because if you look, this is x squared, this is x cubed, and so on, x to the fourth, and so on. All of these numbers are just going to be actual numbers. Those are coefficients. Those are like those C values that we talked about in the previous lesson, how the coefficients can change. All right, the best way to do this is literally just to jump in and do it. So the biggest thing you have to remember is you're going to have to be able to take a bunch of derivatives, and then we're going to have to do some pattern recognition in order for us to be able to write one of these out. Okay, so example 1, it just says, find the Maclaurin polynomials p sub 0, 1, 2, 3, and n for e to the x, and then find the Maclaurin series. So we should all be able to agree that the function e to the x is not a polynomial. It's an exponential. Okay, we all kind of should know what the function e to the x looks like by this point in time, but it is definitely not a polynomial. So in order to create a polynomial using the Maclaurin polynomials, what you're going to need to do is you're going to need to start taking derivatives. So the first thing we need is the original function, f of x equals e to the x. It wants us to find p sub 0. Well, that's actually just the original function. That's the 0th term. We're also going to need p sub 1, 2, and 3. So that means I'm going to need at least 3 derivatives. So I need f prime of x, f double prime of x, f triple prime of x. And then we need the nth derivative. So we're going to need to take the nth derivative of x. And this is a really wonderful one for us to start with because the derivative of e to the x is always e to the x. So that makes that part easy. Every derivative is e to the x. I need all of these evaluated at 0 because that's my center. So we're going to do f of 0. So e to the 0 is 1. We're going to do f prime of 0, which is also 1. As a matter of fact, they're all going to be 1 in this case. Obviously, this is not always going to work out this way. But again, this is why we start with this one. It's just one of the easier ones for us to do. So all of my derivatives are 1. So a polynomial of degree 0, basically, or the nth, or the 0th polynomial of x is just literally that 0th term, the 0th derivative term, meaning you're just actually taking the function evaluated at 0. Well, that's just 1. Okay, that's it. It's the function evaluated at 0. F of 0 is 1. Okay, a polynomial sub 1 of x means, now we have to actually go to the actual definition of the Maclaurin polynomial. It's the first term, which is 1, plus the first derivative at 0, which is 1, over 1 factorial x to the first power. I'm not, well, yeah, I'll write the first power, even though it looks like prime. It's not really the way you want to write it because it does look like a prime there. You write that 1 factorial. So really, that's just going to be the same as 1 plus x. Okay, a polynomial sub 2 of x means it's the first two terms, so 1 plus, and I am going to write these all out actually, so 1 over 1 factorial x to the first plus, again, now it's the second derivative, which is also 1. Now it's over 2 factorial because we're on the second derivative, x squared. Polynomial sub 3 will be 1 plus 1 over 1 factorial x to the first plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. And then the last one, this is the way we're going to have to try and do this to develop these things. We kind of got to figure out what the pattern here is. So the nth polynomial, well, I can rewrite the first so many terms that I have. Okay, we've already done that. That's a factorial there. X squared, 1 over 3 factorial x cubed plus. We're going to take this all the way out to the nth term. So let's see if we can start deciphering the pattern here. The numerator looks like it is always 1 no matter what, so that's not so bad. The denominator looks pretty simple. If we start this pattern at 0, and these all start with n equals 0, this looks like the denominator is 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. So it is literally n factorial in the denominator. And then, as we mentioned before, the factorial and the power of the x, or the exponent of the x, are the same. So that's going to be x to the n power. So that is the nth partial sum. And the nice thing about finding the nth partial sum is it gives you the general term so that you can actually write this as an actual infinite series. So the infinite series now becomes the series as n goes from 0 to infinity. You're just going to use the n term. Instead of writing 1 over n factorial times x to the n, I'm going to throw the x to the n on top and multiply them. So it's going to be x to the n power over n factorial. And that is a power series representation for e to the x. And again, basically what this is doing is it is taking a non-polynomial and creating a polynomial which will hopefully closely approximate that non-polynomial term, that non-polynomial function, excuse me. All right, so as you can see, it's a little bit tedious to write these things out, but this is the process. This is what you have to go through in order to develop these things. So let's try another one. Let's try one for sine of x. Again, kind of picked something here so that it wasn't terribly difficult to take all the derivatives. And we are evaluating all these things at 0 currently, so that's not so bad. So let's see. We've got f of x, which is sine of x. We've got f prime of x, which is then cosine of x. F double prime of x is going to be negative sine of x. F triple prime of x is then going to be negative cosine of x. And we'll go one more at least here. The fourth derivative, remember that goes in parentheses now, is going to bring us all the way back to the original sine of x. And just because I know what's going to happen, I'll take one more derivative, which is then going to be cosine of x again. So that should give us enough to at least get going. Now we need all these derivatives evaluated at 0. So I need f of 0. Well, that's sine of 0. That's 0. I need f prime of 0. That's cosine of 0, which is 1. We need f double prime of 0, which is also 0, because that's still negative sine of 0. We need the third derivative at 0. Let's see, cosine of 0 is 1, but throwing that negative out there makes it negative 1. We need the fourth derivative at 0, which again is going to be 0. And we need the fifth derivative at 0, which is bringing us back to 1 again. So if we want to write the nth term for this thing, because ultimately we're trying to get the series and we need that nth term, let's start writing out the terms that we know. So p sub n of x. Although the first term is 0. The next one will be the first derivative, which is 1, over 1 factorial x to the first power, plus the second derivative, which is 0 over 2 factorial x squared, plus the third derivative, which is negative 1 over 3 factorial x cubed, plus fourth derivative, which is 0 over 4 factorial x to the fourth, fifth derivative, 1 over 5 factorial x to the fifth, and so on. Now, hopefully we can start to see what's happening, and some of you have probably already picked out the pattern here, as far as at least part of it. What you should notice is because I've got zeros on top of those factorials every other term, specifically all of the even exponents, all those zeros are pretty much just going to go away. Okay, so that's gone, that's gone, that's gone. All those even ones are going to go away. So really, it's just the odd ones that we have to focus on for developing this pattern. So let's see. Our nth term. It looks like the numerator is going to be a 1, and then a negative 1, and then a 1, and then it's going to bounce back and forth, which means we need an alternating term. So when we write this, we're going to have a negative 1 to some power. For right now, I'm just going to put the n up there. We may have to make it n plus 1. It'll just depend on how we define this thing. Let's see. Okay, so now we have to talk about the fact that all of the factorials and all of the exponents of x are odd numbers. Okay, in order to get an odd number, you can't use n, because if you use n, it's going to be every number. It's going to be 1, 2, 3, 4, and so on. You can't do n plus 1, because that's still just going to give you every number. It's just going to shift everything up 1 unit. So we have to come up with an expression for an odd number. And this is something that you'll get used to, but the expression to get every odd number is going to be a 2n plus 1. So basically, this is going to have a 2n plus 1 factorial down here in the bottom. And then the x part is going to be the same power, so it'll be x to the 2n plus 1. So now if you think about this, if we start this series at 0, and you plug in a 0 for n, on the numerator you're going to get x to the first, which matches that. On the denominator you're going to get 1 factorial, which matches that. And if I plug the 0 into the -1, it gives me a +1, which matches that. Let's see if it works for the next term. So now we want to try and get an x cubed out of this. So we just plugged in 0, let's plug in 1. So if I now plug in 1, plugging in a 1 into the first n with the -1 will give me the negative, so that's good. Plugging a 1 into the x on top, or not to the x, to the n part with the variable x on top is going to be 2 times 1 is 1, plus 1 more is 3, so that does give me x cubed, which will also give me the 3 factorial. So that is going to be our nth term, or our general expression for the Maclaurin series, which again is centered at 0 for sine of x. So all we have to do now is throw the sum out in front, and n will go from 0 to infinity. And that is a Maclaurin series representation for sine of x. So again, we are creating a polynomial which is going to very closely approximate or become sine of x. All right, not terrible, but again, you can see that I'm trying to help you guys start to develop these patterns. All right, so number 3, find the Maclaurin polynomial for cosine of x. Okay, same exact idea. We could go through this entire process again. It's exactly the same type of process. You're just going to get slightly different values because you're starting with cosine instead of sine, but your derivatives are pretty much going to all be cyclical. It's going to eventually get back to cosine and so on. You're going to have some zeros in there. You could go through the entire process and develop it. Or we can realize that, okay, we've done this kind of thing in the last section. Cosine of x is just the derivative of sine of x. So if that's the case, since cosine of x is the derivative of sine of x, and I now have a representation for sine of x, I can just take the derivative of that power series, and I'll have the power series for cosine of x. Pretty cool stuff there. So let's do that. Let's take the derivative of that power series, and we will get that cosine of x is the series as n goes from 0 to infinity, -1 to the n. Remember, you're only taking the derivative of the x term. The n's have nothing to do with the function of x. So let's see. We'll bring the exponent out to the front, 2n plus 1. Reduce the exponent by 1, brings it down to a 2n. And then we're still going to have that over 2n plus 1 factorial. And that is a power series representation for cosine of x. However, it's going to be simplified just a little bit because if you recognize the numerator has a 2n plus 1, the denominator has a 2n plus 1 factorial. 2n plus 1 factorial by definition is 2n plus 1 times 2n and on down, so that 2n that's left over will be a 2n factorial. So the 2n plus 1 on the top and the bottom cancel out, leaving you with just a 2n factorial in the denominator, which actually makes this a little bit easier to recognize because what you should notice now is that you've got x to the 2n over 2n factorial. So the power and the factorial in the denominator indeed match in this case. Okay, and that will give you all the polynomial terms for cosine of x. So let's go ahead and box that in. So far what we have done just in these first couple pages here is we have created a polynomial representation for e to the x, which is x to the n over n factorial. A polynomial representation for sine of x, which is -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, and a polynomial representation for cosine of x, which is -1 to the n, x to the 2n over 2n factorial. So those last two are very similar to each other. All right, let's go ahead and develop two more. So now we are going to find the Maclaurin polynomial for the arctangent of x. And we'll write the Maclaurin series for that. So what we need, once again, same as before, we need the original function, which is arctangent of x. And we'll need derivatives so we can start developing the pattern. So we know the derivative of arctangent of x is 1 over 1 plus x squared. We know the second derivative of that. Let's see, you could do that either by using a quotient rule or a chain rule. I would probably use a chain rule myself. I would bring that 1 plus x squared up to the top and make it to the negative 1 power. So let's see, bringing that power out to the front is going to make that a negative. It'll be a negative, and then that'll be to the negative 2 power. So it'll be 1 plus x squared in the denominator. But don't forget the chain rule. You got to multiply it by the derivative of the inside, which is going to give you a 2x on the top. And then the third derivative. Okay, right now we don't really have much of a choice. We're going to have to use a quotient rule. And within that quotient rule in the denominator, you're going to have the chain rule again. And I am here to tell you that this one is just too messy to deal with. We don't want to do this. Not that it can't be done, but it is awful. So I am going to give you what the arctangent of x is, instead of us going through the whole process, and tell you that if you were really paying attention yesterday or the previous lesson, that we have already developed this. We just did it in a different way. This was negative 1 to the n, x to the 2n plus 1 over 2n plus 1. I did tell you that star that one, highlight it, whatever, that we were going to come back to that one. And here it is. This is what it ends up being. What you want to notice here is that this one looks extremely similar to the to sine of x. As a matter of fact, they're identical, other than the fact that the 2n plus 1 in the denominator here for arctangent is not a factorial, but it is for sine of x. So if you know one, you pretty much know the other one, as long as you remember that one has the factorial, the other one doesn't. So sine and cosine both have factorials, arctangent does not. But arctangent is identical to the sine of x without that factorial. So that kind of helps as far as memorization type purposes, because you don't want to be developing all these things later on. You're going to want to memorize them. All right, one more, and then we'll call it quits for this video and come back with a second video. All right, let's find the Maclaurin polynomial for 1 over 1 minus x, and then write its series. So let's start off with f of x is 1 over 1 minus x, f prime of x. So let's see, again, that would be the same as 1 minus x to the negative 1 power. So we'll bring the negative 1 out to the front and reduce the power by 1, which means we're going to have something over 1 minus x squared. But then we have to multiply that negative that I'm bringing to the front by the negative 1 from the derivative of the inside, so it just makes it a positive 1 on top. So ultimately, you would get a negative, but it'll become a positive. So second derivative, this one is not as bad as the arctangent because I don't have another function of x on top. I've just got a constant. So again, we can make that a 1 minus x to the negative 2. So you bring the negative 2 out to the front, which is going to give me a negative 2 on top. Reduce the power by 1, we'll get a 1 minus x cubed on the bottom. Then multiply by that negative 1, so now we get a positive 2 on the top. And if you can start figuring out what this pattern is already, that's awesome. I'm going to tell you that the next term is 6 over 1 minus x to the 4th. And then the fourth derivative. If you have already started to figure this out, you'll probably guess that the next one will be 24 over 1 minus x to the 5th, and so on. So now we're going to need all of these derivatives evaluated at 0. And we'll see what we get. All right, the original function at 0, plugging 0 in for x, we just get 1. If I plug in 0 for the derivative, for the first derivative, we're going to get 1 over 1 squared, which is still 1. If we plug in 0 now into the denominator here, well, if you kind of figure this out, every denominator is always going to be 1 raised to a power. So it's just going to be 1, which means that my second derivative will be 2, third derivative will be 6, and the fourth derivative will be 24. So writing these polynomials out, we have to start developing this pattern. So let's see. We're going to get the first term, which is 1, plus first derivative over 1 factorial x to the first power, plus second derivative over 2 factorial x squared, plus third derivative over 3 factorial x cubed, plus fourth derivative over 4 factorial x to the fourth, and so on. I hope you know enough about your factorials at this point that you can start seeing what's happening here. 1 factorial is just 1. So that's going to give me 1 plus 1x, or 1 plus x. 2 factorial is 2 times 1, which is 2. So that's 2 over 2, which once again is 1. So that's x squared. 3 factorial is 3 times 2 times 1, which is 6. So that's 6 over 6, which is x cubed. And you guessed it, 24 over 4 factorial is also 1. So that is x to the fourth, and so on, which means that my ultimate nth term here is just going to be some kind of x to the nth power. And I am hoping that some of you are thinking, well, wait a minute, or maybe you already figured this out before. That looks awfully familiar, and it should, because we already know that 1 over 1 minus x is the sum, as n goes from 0 to infinity, of x to the n. And that's something we did in the previous lesson. All right, that is enough of those specific problems, developing those. I would say that those are probably 5 of the ones that you absolutely need to know. Some of them you should already know. Some of them you can figure out pretty quickly. We'll come back with video number 2 and run through actual Taylor polynomials.